All right, thank you, and thank you to all of the organizers for this wonderful event. I was going to say that if Helen's talk is the prequel, mine's the reboot, because you're going to see a lot of the same characters, but in a very different context. So we've seen a lot about differential privacy as a technology for guaranteeing the privacy of individuals in data analysis. Okay, but mathematically, right, what's developed over the last 10 years is also a very powerful algorithmic toolkit for designing algorithms that satisfy certain stability guarantees. And it turns out that stability guarantees, although they have, as we've seen, a very nice semantic interpretation as a privacy guarantee, can also be useful in other contexts. And what I'm going to talk about today is what's seemingly, at first, a very different problem, the problem of statistical validity in adaptive data analysis. But as we'll see, there's sort of an elegant solution to this problem that goes through differential privacy. And this is going to be a problem that has nothing to do with privacy per se, except that the mathematical toolkit that's been developed over the past decade turns out to be a useful solution. Okay? So here's the cover for an issue of The Economist from earlier this year called Trouble at the Lab. Okay, so you know, even if you haven't read this, you may have come across a bunch of sort of similar hand-wringing in the sort of popular science literature. There's this concern that lots of sort of empirical research, particularly in the medical sciences, is not nearly as reproducible as you would think to look at the reported p-values. Okay, when you see p-values of less than or equal to 0.05, you might expect that 95% of the results you read should be true, should be reproducible. But the number, when you actually go and try to reproduce the published literature, can be sort of less than 50%. Okay, so let me briefly just make the argument via authority. Okay, so John Ioannidis, who was one of the first people to bring this issue into the sort of public psyche, writes that most published research findings are probably false. He's talking specifically about medical research here. Sandy Pentland is quoted in this Economist article as saying that 3/4 of published scientific papers in the field of machine learning are bunk because of overfitting. And Nature News estimates that irreproducible biology research costs are up to $28 billion a year. Cynthia and I recently applied for a grant to study this stuff and argued it would pay for itself. So what I want to talk about is the problem that is known in sort of the empirical sciences literature as the problem of false discovery, and in the machine learning literature as overfitting. These are sort of two sides of the same coin. Okay, so this is not a new topic. I mean, people have been studying how to prevent overfitting and false discovery for decades. Just to sort of name a couple of methods you might have heard of that are aimed at exactly this problem. Okay, there's the holdout method. You can train your model on one part of the data set and then evaluate it on a holdout. There's cross-validation. You can try to control what's called the false discovery rate. You can use the Bonferroni correction, which is a biologist's word for union bound. And one sort of assumption that goes into the analyses of all of these methods is that the data analysis is static. Okay, I'm gonna tell you what I mean by that. Okay, static data analysis is sort of maybe like a model of the scientific method that you learned in 5th grade. Okay, it goes something like this. Okay, first you select your method. You decide what you're gonna do. Okay, then you go out and you gather your data. Okay. You run your method on your data, you test your hypothesis, maybe you get to reject the null hypothesis, maybe not. Okay, so you observe the outcome. But what you are not allowed to do is, after you observe the outcome of your method on the data, after you look at what happened, you're not allowed to go back, change your mind about what you really wanted to look for in that data, and do it again, try it again on the same data. Okay, if you do that, you break the guarantees of all of the methods I just mentioned. Okay? However, it is very natural to want to do that. I mean, we want to do science not in a vacuum, but in a way that's informed by the data. And in fact, I would argue that most empirical science does not work in sort of the way laid out in the textbook scientific method, but rather is adaptive. Meaning, after you observe the outcome, after you plot the data, somehow look at which variables seem most correlated with the thing you're trying to predict, you use that information to inform your method. You select some of the variables and train your models on those, which is to say, you just close the loop here, okay? That the data actually informs the method you're using. Okay, it's a very natural thing to do, but the problem is it breaks the guarantees of most methods of trying to prevent false discovery. Okay, so before I talk about what you might be able to prove in such a setting, I want to lay out a couple of desiderata about what you might want from a theory about adaptive data analysis. Okay, I want to think about, like, what are the various kinds of things we might want such a theory to be able to tell us about. Okay? Now, I think the easiest thing, I'm going to say easy not because actually carrying this out for any particular procedure might be, mathematically easy, but easy in the sense that you can at least imagine straightforwardly how you might, in principle, do it. Right? The easiest thing to analyze is overfitting that results from fixed algorithmic procedures that you can specify exactly. Okay? So for example, you might be doing something like fitting a linear model after you've done some variable selection, where the variable selection is done in a precise way. Maybe you're using the lasso. Okay, so it might be hard to analyze this procedure, but in principle, you could at least imagine rolling up your sleeves and doing it, because ultimately what you're analyzing is a precisely specified algorithm. Okay, there might be some feedback loops in which your algorithm makes sort of changes to the model as a function of the data, but everything's precisely specified. You could, in principle, hope to analyze such a thing. Okay. Maybe a more difficult but sort of equally important problem is what Gelman and Loken, in their very interesting paper called The Garden of the Forking Paths, call researcher degrees of freedom. Okay, and this is sort of the same scenario as in the previous slide, except that the procedure that is making the important adaptive decisions, deciding what variables to include in the model, is not a precisely specified algorithm, but instead the data analyst, some human being who is perhaps, well-intentioned, but not precisely specified. Okay, so this is just don't bother reading the paragraph, but this is an example that Gelman and Loken quote. This is a paper in which a research team is sort of trying to replicate an effect they found among members of the Danish population in sort of members of the American population. So they ask people to take a survey. And what they say here is that initially when you give the same survey to the Americans and run your regression, you don't find the same effect. But that's because questions 5 and 6 refer to have a European market sensibility, and the Americans, probably don't know what those questions mean. So after you remove those two variables and run the regression again, you find the effect. Okay, maybe that was a reasonable thing to do, but it was some variable selection procedure, and it's hard to know what they would have done had the results come out slightly differently. Okay, so we might like to handle this kind of thing as well. And then maybe an even more complicated thing that we'd like to be able to handle, ideally, is multi-researcher reuse of data sets. Okay, so maybe we've got some sort of scientific team here. It's adaptive in a human sense. There are researcher degrees of freedom. They publish a paper. Another researcher comes along and reads the paper, okay, and emails the first team and says, hey, can I thought your paper was really interesting. Can I use your data set? Okay. First researcher obliges. The second researcher runs, his own study. Perhaps he's got his own researcher degrees of freedom, but he's got this other kind of adaptivity, which is that, even if he can precisely analyze everything, all of the adaptivity he himself is employing, he read the paper that came out of the first research group, which was, of course, some ill-specified function of the data. So everything he's doing is not independent of the data, and it's not at all clear how you would hope to analyze this using standard statistical techniques. Okay, and this can continue. Okay, as a homework problem, you might attempt to find the data set that appears in the longest chain of citations, to try to figure out how long this reuse can sometimes be. Okay, so those are the things we'd like to be able to handle. So let's try to distill down what, if we want to be able to talk about all three of those scenarios, what desiderata we might have for a theory of adaptive data analysis. Okay, and these might start to seem like familiar desiderata to those of you who have seen all of the talks today. Okay? So we don't want to artisanally prove theorems about specific algorithms. Okay, we want to have an information measure that is flexible enough to reason about many different algorithms. Okay? We would like robustness to post-processing. Right? That if I tell you that some procedure is safe, I don't want the fact that you sort of puzzled about the results of your study and thought about them and made decisions based on your reflections to ruin those guarantees. Okay, and I want the robustness to post-processing to be both precisely defined post-processing procedures to handle precisely defined adaptivity, but also imprecisely defined. I also want this post-processing to be able to let us talk about researcher degrees of freedom. And finally, I want graceful degradation under composition. Okay, I want, again, to avoid having to sort of artisanally analyze every new procedure. I want that if we have certain building blocks that we've shown to be safe with respect to this goal of adaptive data analysis, that any composition of them should also be safe. Okay, these should seem like familiar desiderata to you because these are all satisfied by differential privacy. And that's going to be one of the important starting points for the connection between differential privacy and adaptive data analysis. Okay, so let me now specify to you, a mathematical problem that we might want to solve. Okay, and in order to clearly specify it, we have to choose a formalism. For most of this talk, I'm going to make some simple choices to tell you to talk about these results in a particularly simple formalism, but I'll tell you at the end how many of these simplifying assumptions aren't really necessary, and that we can talk about correcting for the effects of adaptivity quite generally. Okay, but here's the simple formalism. In statistics, I'm going to talk about a kind of queries that in statistics are called linear functionals, but these are just the counting queries you've been hearing about all day. Okay? So we've got some data universe X. Okay, that's the domain from which points in our data set are drawn. And we've got some distribution P over this data universe. This is the object that as scientists we really care about. Okay, this is representing how the world works. Okay, people are born, they're drawn from this distribution. Okay, so we'd like to learn about this object. But the problem is we do not have direct access to the object we'd like to learn about. We don't have direct access to the distribution. What we have is a data set. Okay, we've got some collection of n points that are sampled independently from this distribution, but our task is to derive conclusions from this data set that hold true with respect to the distribution. Okay, so we've got our distribution, we don't have access to it, we've got a data set which consists of n IID points. So a linear functional, or a counting query, is just some predicate mapping elements of the data universe to real numbers between 0 and 1. Okay? And when I say that what I want to do is learn the value of a linear functional, the value of one of these queries, what's the value? Well, what I mean by the value of a linear functional on the underlying distribution, this is the thing I want to learn, it's just the expected value of this predicate when I draw an element of the data universe from the distribution P. That's the true value for the query. Okay. And our goal is to design statistical estimators, just algorithms, okay, for estimating the values of linear functionals. These algorithms don't have access to the distribution, but they're parameterized by a data set. They can sort of try to derive conclusions from the data set, and they take as input, if you like, streams of these queries and output answers. These are numbers between 0 and 1 that purport to be estimates of the true value of these linear functionals. Okay, so here's the picture. Okay, we've got our distribution, the data set was drawn from it, and we've got our data analyst. Okay? Now, the data analyst is not going to be interacting directly with this distribution, but rather through a statistical estimator, which is which is an algorithm that we get to design. Okay, and the statistical estimator has access only to the data set. Now, the analyst is going to be asking adaptively chosen queries, by which I mean the following. The analyst will pose the first query, and then he will receive an answer from the statistical estimator. As a function of that answer, he will decide on a second query to ask. And again, he'll receive an answer. And this will continue on and on and on until he's finally asked k queries, where the identity of each query asked is allowed to be a function of the answers of all queries previously asked. That's what I mean by adaptive. Okay? And so, you know, that's some problem we might like to solve. Let's agree on a metric of success, a metric to evaluate a statistical estimator. And here's a simple one, which is, you know, essentially just that we can give confidence intervals that hold uniformly around all of the estimates. Okay? So we can say that a statistical estimator is epsilon delta accurate, okay, for a sequence of k adaptively chosen queries, if no matter who the data analyst is, so for all possible data analysts, algorithms for mapping answers to choices of queries, and no matter what the distribution was, so long as the data set was drawn IID from it, we would like that with high probability, with probability 1 minus delta, all of the answers estimated by the algorithm for the queries asked should be within epsilon of their true answers. Okay? So with high probability, the algorithm should give epsilon accurate answers to all of the queries. Okay, so what should we even expect in this setting? Well, let's consider a simple baseline, which is what we could do with sort of a trivial statistical estimator if the queries were non-adaptively chosen. Okay, and by that I mean the setting in which the data analyst ahead of time decides on all k of the queries before he asks any of them, and then receives in sort of one batch answer all k of the answers. So in this setting, you know, none of the identities of the queries do not depend on the answers. Okay? Well, in this setting, there's sort of an obvious statistical estimator to use, right? I'm trying to estimate from data the expected value of some predicate. Well, the empirical average is just the empirical average is an unbiased estimator of this quantity. And because the data is drawn IID, it's concentrated around, its mean is concentrated around the true answer. And so it's not hard to see that, for example, if I wanted to ask k non-adaptively chosen queries, and I wanted to get at most 1% error 99% of the time, that the number of queries the simple empirical average mechanism could answer is exponential in the size of the data set. It is just a Chernoff bound and a union bound. Okay? Unfortunately, it's also not hard to show that the empirical average mechanism is substantially worse when you evaluate it for adaptively chosen queries. Okay, and it's not too hard to argue that there is a reasonable data analyst, not even doing anything too adversarial, that can ask merely linearly many queries rather than exponentially many queries, and cause the algorithm to violate the condition that 99% of the time its errors have only 1% error. Sorry, its answers have only 1% error. Okay, so it seems that adaptivity has an exponential cost in terms of the ability of a statistical estimator to correctly answer linear functionals. Okay? Here we could answer exponentially many queries with the obvious mechanism, and when we introduce adaptivity, you can't answer even linearly many. Okay. By the way, like the reason that the same analysis for the empirical average mechanism no longer goes through is because the empirical average is no longer an unbiased estimator for the true value of this query when the query itself is a function of the data set. Okay, so adaptivity seems hard, but what this claim demonstrates is not that there is no way to correctly answer large numbers of adaptively chosen queries, but just that the empirical average mechanism is a bad way of doing so. It's natural to ask, can we do better with a different statistical estimator? So let me remind you what differential privacy is, and I'll try to emphasize why it's a useful tool for this problem in sort of my reminder. Okay, so differential privacy, and here, again, we don't care about privacy, so you might think of this just as a stability guarantee on an algorithm, promises the following. It's some condition on an algorithm, okay? And we're talking about randomized algorithms which take as input data sets and flip some coins and therefore induce some distribution on their outcomes. Okay, what differential privacy promises is that if I look at the distribution induced by the algorithm when I change one element of the data set, it shouldn't be too far from the distribution induced by the algorithm on the original data set. It's some Lipschitz condition on the mapping between data sets and distributions on outcomes. Okay, and again, just putting this in an inequality that you've seen many times today, more formally, an algorithm is epsilon delta differentially private if for every pair of neighboring data sets that differ in one record, and for every event S, the probability the event occurs when I run the algorithm on data set D is close to the probability that the same event occurs when I run the algorithm on D prime, where close means there's an e to the epsilon multiplicative factor and also a delta term. So what's crucial about this definition for our purposes, okay, also for the purposes of privacy, but for adaptive data analysis as well, is that this is a stability condition explicitly on the distribution over outcomes, not on any metric that we're imposing on the range of the algorithm. Okay? And this is important because it means that if we want to understand post-processing, which is particularly important in our setting in a way that I'll mention in just a moment, we don't need to understand anything about the algorithm or person doing the post-processing. Okay? So this is important because we get this robustness to post-processing. Okay, the claim is that if an algorithm is differentially private and we sort of compose it with any arbitrary function f, then the composition of f and a is also differentially private with the same parameters. Okay? And what's going to be especially important to us is that we have to understand nothing about f. Like this claim is quantified over all f, and so it holds if f is a precisely specified procedure, but even if it's not. Okay? Just to foreshadow a bit, ultimately, what we want to argue is that if we give a data analyst access to a statistical estimator that happens to be differentially private, that the data analyst, no matter what he does, won't be able to overfit the data set. Okay? But the theorem that we actually prove is that if the data analyst himself is a differentially private function of the data, he won't be able to generate a query that overfits the data set. Okay? But there seems to be a disconnect there, right? We want to impose a condition on the statistical estimator and allow for arbitrary data analysts, but the theorem we can ultimately prove is for differentially private data analysts. And it's the post-processing guarantee that makes that connection. Okay, if the data analyst, no matter what he's doing, doesn't have access to the data set except through a differentially private algorithm, then any decision he makes is also differentially private in the data. Okay? This is an important bridge in this setting. Okay? As we've also seen, this distributional stability guarantee degrades gracefully under composition. And this is what Guy told us about, but I want to especially emphasize here that the composition theorems explicitly allow for adaptive composition in a way I'll specify, which is exactly the connection we need for adaptive data analysis. Okay? So what the theorem says is that if we consider the following procedure, where we take as input an arbitrary, human decision maker, say, and then for k rounds, let him choose as an arbitrary function of the results he's already seen some epsilon differentially private algorithm, okay? And then he observes the outcome of that algorithm run on the data set and gets to use that in his future choices. And finally, we'll output the result of all of these computations. Then, no matter who the data analyst was, okay, and for any delta prime we might like to pick, this composition is itself epsilon prime delta prime differentially private, where epsilon prime is a well-behaved function that degrades from epsilon with only, at a rate that's roughly only the square root k of the number of rounds of adaptivity. Okay. So that's great, and the simplest way that Kunal showed us of answering adaptively chosen counting queries, linear functionals, even when the queries could be adaptively chosen, is just by adding Gaussian noise, right? Like an instantiation of the sort of composition experiment from the previous slide is just that every day the data analyst will choose a new query to ask, okay? And the private algorithm that will run is just, the estimate of that query with Gaussian noise. Okay, we'll return to him the exact value of the query plus Gaussian noise, where again the noise has to scale at a rate of square root k. Okay. Well, suppose we asked, how accurate is this algorithm for answering counting queries, not with respect to the underlying distribution, the thing we ultimately care about, but just with respect to the true empirical answers of the queries. Okay, just with respect to the data set. Okay, well, the error introduced with respect to the data set is just the maximum scale of the noise added to any query. Okay, this is Gaussian noise, so it's not hard to see that with respect to the sample, this algorithm is both differentially private and alpha beta accurate, where the error that we introduce is on the order of square root k over epsilon n. Okay? So we get non-trivial error so long as k is smaller than roughly n squared. Okay, but who cares about accuracy on the sample? That's not interesting. The sort of empirical average mechanism gave us perfect accuracy on the sample. So here's the interesting statement. Okay, it's a generic transfer theorem that informally says the following. If you show me an algorithm and it has two properties. Number one, the algorithm is differentially private. But number two, it's also accurate with respect to the empirical answers as evaluated on the sample. Then it will necessarily be accurate with respect to the distribution. It'll necessarily satisfy the accuracy guarantee you really wanted. Okay? It's important that the algorithm satisfy both of these two properties, right? Because the empirical average mechanism was perfectly accurate on the sample, but it wasn't differentially private. It's also very easy to give an algorithm that is differentially private, but not accurate on the sample. I could just throw away the data and respond, with 0.5 every day. What this is saying is if you manage to find an algorithm that is both accurate on the sample and differentially private, that it has good statistical properties. Okay, so let me say that a little more precisely. Suppose A is a statistical estimator for adaptively chosen linear functionals. And let's let P be any distribution over the data universe. Okay? Now suppose we've got a data set that is drawn IID from P. The data set consists of n IID draws from this distribution. Then if we can say both, that the algorithm is differentially private with these parameters, and accurate with respect to the sample with these same parameters, then up to a constant factor loss. It is also accurate with respect to the distribution. Okay? So it reduces the problem of accurately answering with sort of statistical validity guarantees adaptively chosen queries to the problem of privately answering adaptively chosen queries where you only need to guarantee accuracy with respect to the sample. Now, fortunately, there's about a decade of work studying exactly that problem. Kunal told us about some of it. So we even saw, like a couple of slides ago, a particular way to do this, a particular simple way to do this. Rather than responding to every query with its empirical average, first perturb it with a little bit of Gaussian noise and respond with that. Okay, simple algorithm. Just add noise to the queries. Okay, well that's both differentially private and accurate on the sample. And if you combine that simple algorithm with the transfer theorem, then what you obtain is a simple, computationally efficient statistical estimator that can guarantee that for k as large as n squared, it can answer all k of the queries with at most 1% error 99% of the time. Okay? So note that the sort of simple empirical average mechanism, which was exactly the same as this mechanism except it didn't add the noise, was only able to answer linearly many queries. Okay, so immediately you get sort of an improvement in statistical power, a quadratic improvement, simply by adding these small Gaussian perturbations. Okay. We can go beyond that. If you take the state-of-the-art mechanisms for answering differentially private queries, here the one I'm taking is by Hart and Guy Rothblum in the audience, and combine them with this transfer theorem, then you get the following statement. Okay, again, if I want 1% error 99% of the time, then there's actually a statistical estimator that will allow me to answer almost exponentially many queries in n. Let me just explain this log x term, okay, because the previous bounds didn't have them. So here we're paying a little bit for what is log the cardinality of the data domain. You should think about this as the dimension of the data, right? If I have d attributes, then if I appropriately discretize them, the number of possible data points will be exponential in d, and the log of that will be linear in d. Okay, so what this is saying is that if the number of data points you have is substantially larger than the dimension of the data, then the number of queries you can answer, even if they're adaptively chosen, is again exponential, as it was in the non-adaptive case. Okay, so this doesn't tell you much if the number of data points you have is smaller than the dimensionality of your data. But if it's larger than the dimensionality of your data, then we can nearly recover the sort of power that we had for answering non-adaptively chosen queries. We can again answer exponentially many queries. Okay. This is a statement for linear queries. I'm going to talk in a moment about generalizations. Okay. So up until now, I've been sort of restricting attention to these linear functionals. Okay, but let me just tell you sort of a powerful generalization that lets you talk about linear functionals, but also essentially any other data analysis procedure you might be working with, and gives you a method for correcting for the dependence that's introduced between the method you've chosen and the data itself. Right? That was the problem in adaptive data analysis. Right? We've got sort of 100 years of statistics telling us how to analyze various data analysis procedures when the procedure is independent from the data. And the problem we want to solve here is how to analyze the same procedures when the choice of the procedure is a function of the data. Okay? What I'm going to tell you about is sort of a method for reasoning about how differential privacy can help you take the analysis that was intended for the independent case and correct for the effect of the dependence that you're introducing via adaptivity. Okay? So I want to talk about a measure of information which we call approximate max information. Think about this as some kind of worst-case variant of mutual information. Okay, so let me unpack what we're looking at here. Okay, so suppose we've got some joint distribution on two random variables, x and z. Okay, you should probably think about x as the data set and z as the data analysis method that we choose, which might be a function of the data set, which is why x and z are correlated. Okay? Now, what's this notation in the denominator here? X sort of circle cross z. By this, I mean the product distribution that results when I draw x from its marginal distribution and independently draw z from its marginal distribution. Okay? So somehow the quantity in the denominator is the thing that we have 100 years of sort of statistical research to analyze. This is the setting in which the data analysis procedure is actually independent of the data. Okay? In the numerator, we've got the setting we're actually in. We've got the joint distribution between the data and the data analysis procedure, and these things are correlated. Okay? And what max information is bounding is how different these two things can be. Okay? Okay, so that's a definition for a pair of random variables, but we can say also that an algorithm, which maps data sets to outcomes, the algorithm has beta approximate max information, bounded by k, if no matter what the distribution is over the data universe, when we feed the algorithm a data set that consists of n records drawn independently from that distribution, then the beta approximate max information between the random variable representing the data set and the random variable representing the choice of analysis chosen by the algorithm, which is a function of the data set, is at most k. This is some measure. So you can prove that differential privacy bounds approximate max information. Differentially private algorithms satisfy this approximate max information bound. Okay? So to the extent that algorithms that satisfy bounded approximate max information have good properties for any class of statistical analysis methods they might be choosing, differentially private algorithms also have those good properties. Okay. So the reason why max information is the right quantity is it can sort of control the probability of arbitrary bad events that occur as a result of the unwanted dependence between the data and the method of data analysis you've chosen. Okay? Like suppose you've got some bad event that you're worried about. The procedure you ran on the data turns out to give bad results. Well, if you know how to analyze that in the world in which the procedure is independent of the data, then this is telling you that the probability of that same bad event can't be too much worse, even if the data and the analysis method are correlated, if they're correlated only through a differentially private procedure. Okay? So for example, if you wanted to recover the kinds of results we were talking about for linear functionals, this would be your bad event. You'd say, okay, the bad event is that we get a data set and a query, a counting query, such that the value of the empirical value of the counting query on the data set is substantially different than its value on the distribution. Okay, well, when the data set and the query are independent, then we know that this has small probability because of a Chernoff bound. Okay? This is telling us that even if they're not independent, even if the query was chosen adaptively as a function of the data, so long as it was done in a differentially private way, the probability of the bad event is still not very large. Okay? This generalizes, this is the application to linear functionals, but, any analysis for which you can say, the probability of error is small if the analysis was chosen independently of the data, via this connection you can say that the probability of error is still pretty small if there is a dependence, but the dependence is only through a differentially private selection procedure. For example, suppose we wanted to suppose we're empirical scientists and we want to do hypothesis testing. Okay, so we want to reject a null hypothesis. So typically what I would do, I would compute a p-value for my null hypothesis, and if the p-value was smaller than, say, 0.05, I would reject the null hypothesis, and if all of my assumptions were correct and the hypothesis was not chosen as a function of the data, my probability of making a false discovery would be at most 5%. Okay. So I can define a valid p-value correction function for any selection procedure A. Okay? A correction function is valid if for any level of statistical significance alpha that I like, the following procedure, which first computes the test statistic of interest and the corresponding null hypothesis, or selects the test statistic as a function of the data by running A on the data set and a corresponding null hypothesis, okay? And then computes the p-value that results from that test statistic, ignoring the dependence between the hypothesis and the data. So I compute the p-value as if the hypothesis were independent of the data. But then I only reject the null hypothesis if the p-value is not smaller than alpha, but smaller than the corrected value of alpha. And I'll call such a correction function valid if indeed the probability of making a false discovery when running this procedure is at most alpha. Okay. So what is almost immediate from the definition of max information is that if the selection procedure satisfies an approximate max information bound of k, then essentially simply dividing my significance level by 2 to the k results in a valid p-value correction function. Okay? So just putting it all together, if you're selecting your hypothesis, if you're selecting hypothesis tests now, these can be arbitrary hypothesis tests. They don't have to be, based on linear functionals. If your access to the data is limited to a differentially private procedure, then you can correct for the effects of adaptivity and still result in statistically valid inferences, okay, with some particular parameters. Okay, so John raised the bar by putting a plot on his slides, so I feel that I should do the same. So let me tell you about a particular simple but hopefully useful application of this kind of result, okay, for producing what we call a reusable holdout. Okay, so the holdout method is the following. It's a sort of simple procedure for trying to avoid overfitting. I take my data set, I split it in two, I train my model by doing whatever I like on the training set, and then I evaluate it on the holdout set. Okay? That works because I've held out the holdout set, no matter what I did on the training set, the holdout set is independent of the model I selected. The problem is, I can't then, if I don't like the results, go back, retrain, and test again on the holdout set. If I wanted to have another round of adaptivity, I would need another holdout set, and that would cause my data demands to sort of grow linearly in the amount of adaptivity. Okay, so the question is, can we use these techniques to have a holdout set that we can reuse adaptively many times? Okay. So you can. So here's an algorithm. When I gave this as a tutorial at ICML, it was natural to show this as Python code, possibly less natural at IAS. But the algorithm's extremely simple. Okay? Let's talk about it for linear queries. The analyst asks a query. The algorithm evaluates the empirical value of that query, both on the holdout set and on the training set. Okay? And then it computes how different those two things are. What is the absolute value difference between the value of the query on the training set and the holdout set? And it adds some noise to that for differential privacy. Okay? And if that noisy value is below a threshold, okay, if the difference between the value of the query on the holdout set and the training set is small, then it says, okay, there's no need to waste information about the holdout set on this query. You already know a good answer, the value of your query on the training set, and it just tells you that. It says, look inwards. The answer you seek is in the training set. However, it might be that you've overfit the training set and you've asked a query whose answer is substantially different on the holdout set. In that case, it perturbs the answer on the holdout set in order to guarantee differential privacy and gives you that. Okay. So what does this algorithm guarantee? I'm not going to tell you the precise guarantee, which is a little technical, but roughly it tells you something like this. It says if you want, for example, 1% error 99% of the time, then you can keep asking queries, okay, for possibly an arbitrarily long time. However, like occasionally you will ask queries, you can keep asking queries for a long time so long as you haven't actually overfit the training set. Okay, so long as, this algorithm, whenever you ask a query, is answering it with, in the first manner by telling you the value on the training set. Okay, occasionally you will ask a query that actually does overfit the training set, forcing this algorithm to release information about the holdout set, to release the answer on the holdout set with Gaussian noise. And what the theorem roughly says is you can keep asking queries until the number of queries you've asked that actually overfit in this way is n squared. It could be that that's every query, in which case this algorithm really just reduces to adding Gaussian noise. If every query is answered on the holdout set, then we're just using the Gaussian mechanism on the holdout set. We're adding Gaussian noise every time, and we inherit the guarantee of the Gaussian mechanism that you can answer n squared queries. But if you're lucky, not every query overfits. You're not in the worst case, and you can answer more queries. Okay, so here's what the plot's going to show. And I should again add the caveat that this is, like a simple numerical experiment. We didn't do anything with a real data set. So we've got a data set that we generated with 20,000 rows and 10,000 features. Okay, and class labels are binary, -1 or 1. And the analyst is doing something simple, stepwise variable selection. Okay, so think about the analyst as first trying to select relevant variables and then fit a linear model to the data set. Okay, so the analyst splits the data into a training and holdout set by just dividing it in two. And then he tries to find the best k variables on the data set, those variables that are most correlated with the label. Okay, but he's aware of, like the potential to overfit the training set, and so every time he finds a variable that he thinks is highly correlated on the training set, he only keeps it if it also is highly correlated on the holdout set. Okay, and after he selects these k variables, he'll fit an ordinary least squares model. He'll try to train a linear predictor. Okay, and along the way, he might try to find the best number of variables to use in his model. Okay, so there's two pictures I want to show you, okay, that sort of correspond to arguing that this procedure, number 1, successfully prevents overfitting, but number 2 allows you to find signal when it is in the data. Okay, so here's the first picture in which there really is no signal in the data. Okay, the data are totally random in that their labels are independent of the features. Okay, there is just no way to predict the labels from the features. Okay, so I want to show you what happens using the standard holdout method and using the reusable holdout method. And what are these lines? So the red line is the real error rate of the linear model learned. Okay? In this setting, every model has error 50% because the labels are actually independent of the features. Okay? The blue line is the apparent error rate on the training set, and the green line is the apparent error rate on the holdout set. Okay? So you see when we use the standard holdout method, the analyst greatly overfits the training set, but more importantly, cannot detect this overfitting because he's also overfitting the holdout set. Okay? However, when we use the reusable holdout method, the analyst continues, of course, to overfit the training set, but is able to identify his mistake because the error estimated on the holdout set continues to be the correct error. Okay. So we can correctly detect overfitting. One more picture, okay? Suppose there actually is a signal in the data. Okay, so the same setting, but we've got 20 features that have a mild correlation with the target. Okay, and the remaining features are uncorrelated. Okay. Well, again, with the standard holdout method, we overfit the training set, and when we try to look at the holdout set to determine what value of k should we choose, what's the right number of variables in our model, the maximum value is 500. And importantly, note that the error we estimate on the holdout set does not track the true error. However, when we run the same experiment with the reusable holdout method, of course, we overfit the training set, but the error estimated on the holdout set tracks the true error, and in particular, we correctly detect the right model size. All right. Okay, so the slides are going to be available online afterwards, and you can, all of these mysterious sort of collections of letters and numbers that I put up, you can see the papers they correspond to, but that's it, and thank you very much.